Alrighty, folks, we are beginning the sixth main chapter slash phase of the course, talking about what are called eigenvalues and eigenvectors of a matrix. So we'll start out by talking about what these are, and then over the course of the next several lessons, we'll talk about how these things are used in mathematical and in real-world applications. So, first of all, what is an eigenvalue and what is an eigenvector of a matrix A? If you're dealing with a matrix A, an eigenvector is a non-zero vector V that is scaled by the action of A. A times V is equal to some scalar multiple of V. This is the definition of an eigenvector of a matrix A. It is a vector that is scaled by the matrix A. And if you have an eigenvector that is satisfying this equation, AV equals lambda times V. Lambda here is what we call the eigenvalue associated with this eigenvector. So that's the definition of these terms. So for example, here, suppose that we have the matrix -1, 1, 4, -1. I claim that the vector 1, -2 is a special vector which is scaled when multiplied by this matrix A. So let's go ahead and verify that, and let's find the corresponding eigenvalue. To verify that, I'm going to apply the matrix A to the vector, and I'm going to see what happens. So the matrix A multiplied by the vector V, following the normal matrix multiplication process, would be -2 -1, result -3. And then in the second row, it's going to be 4 plus 2, 4 plus 2, giving me 6. So this result, -3, 6, is equal to a scalar multiple of our original vector. Specifically, if we take our original vector and scale it by a factor of -3, then that's equivalent to this result that we've gotten in the center. So as a result, we can say that this is an eigenvector of our matrix because this vector was scaled by the action of the matrix. And not only that, we can also say that the corresponding eigenvalue is -3. Let's also verify that the vector 1, +2 is an eigenvector of this matrix. And then let's find the corresponding eigenvalue. So once again, to verify that result and to find the corresponding eigenvalue, all we have to do is multiply the vector by the matrix and see what happens. So we have -1 plus 2, giving us 1. Then we have +4 minus 2, result 2. So what we've gotten here is actually pretty interesting. What we've gotten is an exact copy of the vector that we originally had. So we can think about this as the number 1 times the vector 1, 2. And so we do have an eigenvector in this case, and the eigenvalue would be equal to +1 here, because A times V is equal to 1 times V. Now, if you are given a matrix A, how can you calculate the eigenvalues and how can you calculate the eigenvectors from scratch? To explain how to calculate eigenvalues and eigenvectors from scratch, let's go ahead and look at this equation AV equals lambda V, which we gave earlier in our definition of eigenvector. Let's take this equation and let's rewrite it a little bit. The first thing that I would like to do is I would like to subtract the vector lambda V from both sides. So that turns this equation into AV minus lambda V equals the 0 vector on the right side. Now both of the terms on the left contain a copy of the vector V. And I would like to, in some sense, factor out the vector V from this expression. I have to be careful when I do this because if I just write an expression A minus lambda quantity times V, what I've written right here doesn't make any sense. What I've written right here is has a syntax error. It has a syntax error because this subtraction matrix minus number is not defined. We don't have a way of taking a matrix and subtracting a scalar from that matrix. There's a type mismatch here. So I would still like to try and factor out V, but I have to be careful how I do it. This is not the correct way to factor out V. Let's think about what would be the correct way to factor out V. Over to the side, I'm going to think about the matrix. I'm going to think about the matrix lambda times the identity. Lambda times 1, 1, 0, 0, for example. Lambda times the identity is a matrix that when multiplied by any given vector has the same effect of scaling a vector. And so instead of thinking about this term as lambda v, I'm going to think about this term as lambda times the identity times v. And the reason why I'm going to do that is because when I think about this expression with the identity matrix in there, when I factor that out, A minus lambda times the identity actually is well defined. This is the correct way to quote unquote factor out V from this equation because the quantity that it leaves behind in the parenthesis is well defined because you're taking a matrix A and you're subtracting another matrix. So just by putting the identity into the equation, we make it well defined, we eliminate that syntax error, but it's still equivalent to the green equation that we have above. Now, the reason why I rewrote this equation in this format is because now when I have an equation that looks a lot like something related to the null space. From this equation, we see that the matrix A minus lambda I contains the eigenvector V in its null space. Now remember that the eigenvectors of a matrix are defined to be non-zero. So that means that A minus lambda times the identity has a non-zero vector in its null space. And that brings us back to some of the results that we got when we studied invertible matrices and the invertible matrix theorem in the previous chapter. When we studied invertible matrices, we saw that an invertible matrix was only allowed to have a trivial null space. An invertible matrix was only allowed to have 0 in the null space. And so because our matrix has a non-zero vector in its null space, our matrix A minus lambda I must be singular. And because this matrix is singular, again, going back to invertible matrix theorem, a singular matrix has a determinant of 0. And so here is the major takeaway and the major conclusion from this work that we've done. If you have a matrix A with an eigenvector V and an eigenvalue lambda, that matrix must satisfy the equation that the determinant of A minus lambda I must be equal to 0. This equation is satisfied for any value lambda that is an eigenvalue of your matrix. So let's go ahead and use this principle about the determinant and to use this principle about the null space to help us to find eigenvalues and eigenvectors of a matrix from scratch. When we're trying to find the eigenvalues and the eigenvectors of a given matrix A, the first thing that we do is set up this matrix A minus lambda times the identity. We will set lambda as a variable, and then we will try to solve for the values of lambda. For example, suppose that I give you this matrix A being -1, -4, -3, -2. If someone wants me to find the eigenvalues of this matrix, the very first thing that I would do is I would calculate A minus lambda times the identity. The matrix -1, -4, -3, -2, take away lambda times the identity matrix of the same size, 1, 0, 0, 1. Now, if we use PEMDAS to complete that calculation, starting by scaling the identity matrix by lambda, and then subtracting these two matrices from each other, I get in the top left -1 minus lambda, then -4 minus 0, then -3, and then -2 minus lambda. So here is the matrix A minus lambda times I. And notice that at the end of the day, A minus lambda times I really amounts to subtracting lambda from the diagonal entries of your matrix. Now, let's go ahead and calculate the determinant of this matrix and set the result equal to 0. We'll set the determinant equal to 0 to find the values of lambda that make A minus lambda I into a singular matrix. Those values of lambda will be our eigenvalues. So let's go ahead and find the determinant. So using the standard determinant process here, if I multiply these entries on the main diagonal, I get -1 minus lambda, -2 minus lambda, and then subtract what I get on the anti-diagonal, minus -3, -4. So I get lambda squared plus 2 lambda. I get plus 1 lambda plus 2 from foiling out that first product. And then in the back, I get -12. If I simplify that, I get lambda squared plus 3 lambda and then minus 10. I'm going to take this determinant and I'm going to set it equal to 0. And this will allow me to find the values of lambda that make this matrix singular. And those will be our eigenvalues. I can solve this equation, for example, by factoring. And I can say lambda plus 5, lambda minus 2 must be equal to 0. And that means that I get one value of lambda being positive 2 and another value of lambda being -5. And these are the so-called eigenvalues of our matrix A. So by subtracting lambda from the diagonal, finding the determinant of the result, and setting that equal to 0 and solving for lambda, this allows you to find a matrix's eigenvalues from scratch. So having now found the eigenvalues, let's go ahead and find the associated eigenvectors. Let's go ahead and find the v's that go with these lambdas. Having identified my first lambda value as lambda 1 equals 2, to find the associated eigenvector, I'm going to use this property that we established earlier. If lambda is an eigenvalue associated with eigenvector v, then the eigenvector must be in the null space of this matrix, A minus lambda times I. So what I'm going to do is I'm going to calculate a minus lambda 1 times I. I'm going to calculate a minus 2 times I, and I'm going to look in the null space of that matrix for the eigenvectors. Now, a minus 2 times I is going to work out to be the matrix A with the value 2 subtracted from the diagonal entries. So we're going to have negative 1 minus 2 in the upper left position. The entries that are off the diagonal will be unaffected, and then the value of minus 2 on the diagonal will get subtracted again. Minus 2, minus 2. Negative 3, negative 4, negative 3, negative 4. So this is the matrix A minus 2 times I, and the eigenvectors corresponding to this eigenvalue are going to be whatever is the null space of this matrix. So we can find the null space in the normal way. We can, for example, augment this matrix with 0 to see what kind of inputs would give rise to a result of 0. If we do row reduction, the two rows are just scalar multiples of each other. So the entire bottom row would become 0. And so we're left with a single meaningful row corresponding to a single meaningful equation that I might write down as negative 3x1 minus 4x2 equals 0. X2 is free. As we've done before, we can rewrite these equations to express everything in terms of the free variable. For example, I can solve the first equation and rewrite it as x1 equals negative 4 over 3x2. And I can rewrite x2 equals as just itself, x2 equals x2. All the vectors in the null space of a minus 2i. In other words, all the eigenvectors corresponding to an eigenvalue of lambda equals 2, they're all the vectors of the following format. Some number times negative 4/3 in the top entry, 1 in the bottom entry, or in other words, the span of negative 4/3 comma 1. So these are all the eigenvectors of the matrix A associated with this particular eigenvalue. The eigenvectors associated with this eigenvalue are all the vectors of the form some number times negative 4/3 and 1. Similarly, we can find and we can describe all the eigenvectors associated with the other eigenvalue. If I want to find the eigenvectors that are associated with lambda 2 equals the other value, which was negative 5, I need to take my matrix A and I need to subtract this one particular eigenvalue that I'm studying right now, A minus negative 5 times I. In other words, A plus 5 times I, and then I need to look at the null space of that matrix. So in other words, I need to go into the matrix A and I need to add the number 5 to each of the diagonal entries. Negative 1 plus 5, the entries negative 4 and negative 3 are unchanged. And then in the bottom right corner, negative 2 plus 5. So after simplification, this gives me the matrix 4, minus 4, negative 3, and 3. And notice once again, of course, in this case, one of our rows is going to be redundant, right? As we row reduce the augmented matrix corresponding to a null space calculation, This entire bottom row is just a scalar multiple of the entire top row. So only the top row is contributing meaningfully to this problem. If I interpret this result, this first row is telling me that 4x1 minus 4x2 is equal to 0, and x2 is free, an equation which can be rewritten to express everything in terms of the free variable. That first equation says x1 and x2 must be equal. That second equation says x2 can be whatever. x2 is just equal to itself. So the null space of A minus negative 5 times lambda, which is the set of the eigenvectors corresponding to an eigenvalue of negative 5, we can find that all of those eigenvectors have the format x2 times 1, 1, or in other words, all the vectors that are spanned by 1, 1. So this is how, given a matrix A, you can find its eigenvalues and its eigenvectors from scratch. First, set up a variable lambda and calculate the expression A minus lambda times I, which effectively means subtracting lambda from the diagonal of the matrix. Once you've done that, find the determinant of A minus lambda I and set that result equal to 0. The solutions to that equation, the values of lambda found, will be the eigenvalues of your matrix. Now, once you've found the eigenvalues from this determinant calculation, one by one, go ahead and find the associated eigenvectors. For example, to find the eigenvectors associated with the specific eigenvalue of 2, go back into your matrix A minus 2 times I and look at its null space. The null space of this matrix A minus 2 times I is going to be the set of all the eigenvectors associated with 2. Some terminology associated with these calculations. When we write down this equation, determinant of A minus lambda I equals 0, this equation that we write down to help us to find the eigenvalues and solve for lambda, this guy is called the characteristic polynomial. We've also noticed that when we're going to find the eigenvectors associated with any particular value of lambda, any particular value of lambda gives rise to an entire set of eigenvectors. So because of that, and because this set corresponds to the null space of a certain matrix, this particular set of eigenvectors is sometimes called an eigenspace. So that concludes today's material. We talked about what is an eigenvector of a matrix. An eigenvector of a matrix is a vector that is scaled by the action of the matrix and satisfies A times V equals lambda times V. Now, if you're given a vector and you want to check, see, is this an eigenvector or not, all you have to do is multiply that vector by the matrix and see what happens. Did the matrix scale the vector or did it do something else? If it scaled the vector, then that vector is an eigenvector. If you have to find the eigenvectors and the eigenvalues from scratch, then you can do that by calculating A minus lambda I, calculating the determinant of that, setting that equal to 0, and solving for lambda. Those are going to give you the eigenvalues of your matrix. And then for each value of lambda, for each eigenvalue, go and calculate A minus lambda I and calculate that matrix's null space. The null space of this matrix is equal to the set of the eigenvectors corresponding to whatever is your lambda value.